All right. Oh, what is going on? All right. Okay. Good afternoon, everyone. Let's start. Yeah. So first of all, please start thinking about the project selection, right? And by the way, if you have made a decision, please upload a PDF to the Canvas. Don't send me the email, because we're gonna. I mean, at some time point, our TM is gonna do this all together and just count and make the statistics about who are gonna do research project, who are gonna do paper rating. So don't just send me an email telling us you want to do this, you want to do that. So just summarize. I mean, make a Word document and then save it as a PDF and upload to the Canvas, because that is created as assignment. Okay. So let us continue with the fundamental or commonly used probability distributions.
What should that PDF say? Just the member of our team?
I think if you can take a look at the assignment requirement in the Canvas, it just asks you to provide which project type. If you want to do a research project, indicate your team members. If you want to do the paper rating, just grab 3 papers list. I mean, that's not, the paper list is not necessary to be, I mean, unchanged throughout semester. You can just grab 3 papers list there, and then later you can freely change it as long as you have enough time. Okay. So any other question regarding the project and the homework? Okay. So in the last lecture, we first talked about a few discrete distributions, right? So the most commonly used one for binary variables, right? Bernoulli experiment, right? And Bernoulli experiment usually, I mean, we use some Bernoulli distribution to model it. Like you toss a coin, it's head up or tail up, right? And then we can extend the Bernoulli experiment to binomial experiments. So that's basically saying, okay, I want to do the independent trials of Bernoulli experiments for n times. Then how many ones are in total? Right? And then we extend the binary distribution to like categorical distribution. Like suppose you're rolling a die, you have 6 possible outcomes, right? 1, 2, 3, 4, 2, 5, and 6. And then how do we make work out a distribution to model the generation of this categorical outcomes? Most commonly used one is called categorical distribution, right? So we talk about one-hot encoding. Why we use one-hot encoding? By the way, one-hot encoding is just like k-dimensional vector. There is only one non-zero element, and all the other elements are 0. So this is just for convenience. When you derive something, when you write down the probability distribution, you can put the value of this one-hot encoding on the power. So it's very convenient for you to do the maximum likelihood estimation and etc. Right? And correspondingly, we can extend the categorical distribution to multinomial distribution. So it's basically like if each single experiment I'm doing some kind of categorical experiment, right? Each single experiment I just roll a die, I got 0.1. Next time I got 0.6, and next time I got 0.2. Right? Suppose I kind of repeat experiments independently for 100 times. Then what is the distribution of the count of each category, right? So suppose you roll a die for 100 times. Now how many times you're gonna observe 0.1? How many times you're gonna observe 0.6, right? So this counts across these k categories will follow the so-called multinomial distribution. Right? We talk about how to obtain its probability distribution. So basically, you can imagine each single realization follows some categorical distribution, but many different realizations may correspond to the same outcome. like if you have a 0.1, right? Yeah, if you have the same 0.1, right? Maybe your first experiment and third experiment you also see this, right? So you have to count all possible realizations which give you the same outcome. That's why we need to multiply some combinatorial number, right? So this is just to give you a quick refreshment. But when you, if you want to look at, if you want to write down the details, you need to look at the math, right? So, and then an interesting question will be, okay, so if we go back to the Bernoulli distribution, right? So we know that if your observation is a binary, right? Either 1 or 0, like the outcome of your tossing corn experiment, right? We know that we can use a Bernoulli distribution to model X, right? Which describes how likely, what's the likelihood of your particular observation for X, right? So we know that this distribution is parameterized by this probability mu, right? Mu actually indicates the chance that you observe 1, right? Or you observe head up, right? So then a natural question would be like, if I want to add one more hierarchy, right? I want to know if I want to assign my prior knowledge about this mu. How can we do that? So now we're going to assign probability over the probability, right? So this mu is between 0 and 1, right? So mu indicates the chance you observe your corn having the head up, right? So you want to assign a probability distribution over mu. It's not over X. So mu here is continuous, right? So the most commonly used distribution for this single probability is the beta distribution, right? So in the last lecture, we talked about the probability density of the beta distribution, right? So just to be pay attention to the beta distribution. So first, the mu here is a continuous number. It's between 0 and 1. So this is a continuous distribution. So this is not a Bernoulli distribution. Bernoulli distribution is for binary variable, or in other words, for discrete variable. But then when we model the distribution over the probability mu itself, it becomes a continuous distribution, but restricted. But the mu must be restricted between 0 and 1, right? So this is something I hope everyone won't be confused, right? So, and this is the form. You don't need to memorize that form, but just to be aware, beta distributions looks like that, right? And you see a beta distribution is parameterized by 2 parameters, A and B, and different choices of A and B will lead to different density functions. Okay. And here are nice properties about beta distribution. A common use properties of beta distribution, like expectation of mu is A over A plus B, and the variance is something like this, right? So now, here I want to point out the fact that beta distribution is important because it is a conjugate prior to the Bernoulli likelihood. Right? So as to what is conjugate, we're going to give some definition later. But you can view like if I have a Bernoulli likelihood to model my binary observations, and if I assign a beta distribution, beta prior distribution over this probability in your Bernoulli likelihood, and then the computation of the posterior distribution will be a lot easier. A and B is just parameters which determine the beta distribution. No, you shouldn't view as a standard deviation because you know, if you want to compute the mean and the variance for mu, they need to involve both A and B. So this is not so we shouldn't like make it contrast to Gaussian distribution. It's not like that. It's just like parameters which determines this distribution. Oh yeah, there's some interpretation on that, but it's not required in this class. If you're interested, you can take a look at that. But then it's not. I mean, like when we talk about gamma distribution or the different parameterization, if you have different parameterization that correspond different meaning, it comes from like biostatistical literature, because they want to model a specific type of random phenomenon, so they derive this kind of stuff. But for us, you just need to know, okay, they have these two parameters. You have to be sure that A and B are positive. Any other question? Okay, so we're going to talk about the conjugate prior. What is conjugate prior? This is actually very, very important in Bayesian statistical literature. Now, let us consider the general categorical case, right? So if I have a categorical random variable which can take k possible values, right? So we know that to model such a random variable, right, we can use a categorical distribution, which is determined by this probability vector, right? So mu1 to mu k, for example, if you have 3 categories in total, right? So it might come from, I can construct a distribution for your categorical variable. It might be 0.1, 0.2, and 0.7, right? So this can be an instance or instantiation of your mu, right? It's an actual probability vector. And under this probability vector, you got a chance like 0.1 to generate categorical 1, right? 0.2 to generate categorical 2, and 0.7 to generate categorical 3, right? So the random variable x here, remember it is represented by 1-hot encoding, right? So the probability that x takes each particular category is determined by the corresponding element in this mu vector, right? So the follow-up question will be, okay, if I want to assign a probability over mu itself, what kind of distribution is appropriate, right? So sometimes people refer to this kind of distribution as distribution of distributions. Why? Because mu itself is a distribution. It's just a discrete distribution over k possible values, right? So now I want to assign the probability distribution over mu itself, right? So the most commonly used such distribution is called Dirichlet distribution. So you can view like beta distribution as a special instance of Dirichlet distribution. So here is the definition of the density of the Dirichlet distribution. So you can view like controlled by a k-dimensional parameter vector alpha. Of course, you're gonna ensure each alpha k is positive, right? And then you can sample a probability vector mu with this density. So you can see the form is kind of pretty similar to the probability of discrete or categorical variable. So, but right now, you gotta have a mu k as the base, right? And you take the power of the parameter alpha k minus 1, right? And you just multiply over all possible categories in your distribution, right? And this guy is corresponding to the normalizer. So you can see that this is actually, I mean, it's pretty easy to memorize that, although it's not required. So you can view like you see that this is a product, right? It's product of each term regarding mu k, right? So in the denominator, this is also product over the each parameter alpha, right? Gamma alpha 1 times gamma alpha 2 until gamma alpha k, right? And in the numerator, it's just the gamma of the summation of those parameters.
So we use this solution as a trial method. We want to trial categorical distribution. Right?
Yes.
So we mean that when UK is bigger than 1, it is 0. Yeah? It is defined only on change dimension of this.
Yeah, mu k couldn't be bigger than 1. So there, all of these samples will satisfy that your mu k is a probability vector. It's not like free continuous vectors.
So out of this distribution is set to 0.
No, it's not all of this. You can't sample from all of this. I mean, you can't sample mu which doesn't satisfy the probability constraint. Okay. Like in other words, like support of the.
I mean that if we want to integrate this, we should integrate it for all R K or just on
Just under 0 and 1.
yeah.
Yeah, with the constraint that you have this summation. This definition is definition of the domain where on mu you can integrate is called a simplex, but we're going to talk about right now. Okay. So here is some like graphical illustration of the Dirichlet distribution. So we talk about 3 variables, mu1, mu2, and mu3, as we just discussed, right? So the sample for a Dirichlet distribution will always be a probability vector, meaning that your mu1, mu2, and mu3, the summation must be 1, and each of them must be bigger than 0, no less than 0, and no bigger than 1. Okay. So, and for the 3-dimensional case, meaning that you have 3 variables, this domain, or I think you should say it's a support, is actually simplex. So simplex means it's just a subset of a plane where each point on this plane will satisfy this probability constraint. But if you have 2 variables, right? If you have 2 variables, then it is just a line segment. Why? Because mu1 plus mu2 equals to 1, right? So if you write it down as mu2 and mu1, this is actually a line segment because you need to ensure that mu1 and mu2 are non-negative, right? They can only be here and here. Right? So it's not hard to verify that the beta distribution as a special case of Dirichlet distribution will take k to be 2. Any questions so far? Hopefully this is kind of natural to everyone because it's just an extension of beta distribution. Okay, so and here are the important properties of a Dirichlet distribution. So the expectation is actually, the corresponding alpha proportional to a corresponding alpha. So you just divide alpha k, or sorry, this is alpha, it's not a, by the summation of all the parameters. Okay? And here is one interesting property about Dirichlet distribution when we talk about topic models. You need to compute expectation of the logarithm of this mu k. Right? So if you want to take that, as long as you know the parameters, this is given by this digamma function. So digamma alpha k is subtracted by digamma summation of all the parameters. So digamma is defined as the derivative of logarithm of gamma function. So this form seems a little bit weird, but you don't need to worry about how to compute that, because all the modern numerical libraries will support that. It will give you, like if you look at SciPy or NumPy, they have some functions called digamma, or PyTorch or TensorFlow. They all provide the library to compute this function and its derivative. Okay, similarly to the case of beta distribution, Dirichlet distribution is a conjugate prior to the categorical likelihood. So that means if your model assign a Dirichlet distribution over your probability vector, and with this probability vector, you sample the categorical variables, and once you get the data, if you want to compute the posterior distribution of your probability vector, it has closed form. That's the benefit of using conjugate prior. But we're going to give the definition of conjugate prior later. So any question so far? Well, you can imagine that, okay, suppose I can choose alpha is 1, 1, 1, right? For the 3 categories. Right? I can define such a Dirichlet distribution. Imagine if you use this Dirichlet distribution to sample, to generate samples, what are the possible samples on that, right? So, I mean, you can imagine it could be 0.2, 0.2, 0.6, it could be 0.7, 0.2, 0.1, could be 0.1, 0.5, 0.4, right? You can use that to generate, different probability vectors. And then given these probability vectors, then you can sample the observed categories. Right? Like if you want to roll a die, right? If you, for example, if you have some prior knowledge about how likely each point will show up, right? For example, I believe point 3 has larger chance to appear. I can assign a probability, Dirichlet prior distribution over my probability vector. I just run them, right? A few numbers, like maybe 0, 1, 0, 1, 0 0.3, 0 0.1, 3, 4, 1, 1, 2, 3, 4, 5, 6. Am I correct? Oh, this should be 5, right? So, so you can use this as your parameter of your Dirichlet distribution, and then you use that to sample your probability vector. Well, on average, it will give you probability vector where the chance of the 0.3 showing up is larger, right? So, and then if you want to go back to infer the probability vector given like 1,000 times of gambling, then you can combine this prior and your observation to infer that. Does it make sense? Okay. So here I just want to briefly mention the application of this Dirichlet distribution. Right? So maybe you guys have heard them before. Maybe like 10 years or 15 years ago, there's a very popular machine learning model. It's called latent Dirichlet allocations. So basically, it wants to address a problem. It's actually a very important problem in text mining, information retrieval system. They want to I mean, from a collection of the documents, newspapers or bloggers, whatever, they want to extract topics, and those topics are usually represented by the keywords. For example, if you download the news text from like New York Post or whatever website, right? You can imagine, okay, it must cover, those news must cover many topics like politics, like sports, like financial things, right? So it's always important to find, okay, how many topics do these corpus or do this collection of documents contain? And second, to represent each topic, what are the important keywords? Like if you're talking about financial, if we talk about arts, for example, maybe in this particular document set, they're gonna frequently use musical, actor, opera, actress, those kind of words, right? And when we talk about education, you may talk about education, teachers, public, and benefit, president, elementary, such kind of things. So if once you can extract those keywords, it will be very helpful to give you better search results. So before the coming out of this LDA model, doing this kind of challenging things. So because from this collection of the documents, how do you decide, how do you automatically extract these keywords unless you do this manually? And then LDA or latent direction allocation can help you automatically find out the keywords that can represent those different topics. So it was very popular for a long time, right? And right now people have saying this, will this problem has been resolved? Okay. So and the key idea, I mean, key modeling component of this model is the Dirichlet distribution. So you can imagine each of these words, right, on a different topic. You can see because words are discrete, right? So as long as you have vocabulary, you can view like the appearance of each word is actually one particular category. So the generation of those topic keywords can be viewed as a realization of the Dirichlet distribution. And then just play a mixture of this Dirichlet distribution because they come from different topics, right? And then once you got this observed data, you can view like, okay, it is just the generation of a mixture of Dirichlet distribution. Now I want to revertly infer which particular what is each particular Dirichlet distribution is. That is called LD or latent Dirichlet allocation. And those different colors just represent different topic words. Yeah, we'll go to this later. As one example, when we talk about hierarchical Bayesian model and graphic models, we'll use as one example to show how this whole model is built up and how do we do efficient inference on that. But I just want to highlight that the Dirichlet distribution can be really beneficial. And we're going to also talk about the problem, I mean, the limitation of using Dirichlet distribution. That's why in Google, they developed another type of system. It's not Dirichlet distribution to extract those topic words. Believe me, this is very fundamental, important problems. If you can't do this well, you cannot be a successful search engine. Okay, so now let us talk about continuous random variables, right? So we're going to start with the Gaussian distribution. I believe everyone knows this and everyone's familiar with this. So for the single variable case, I bet everyone is able to write down the density, right? So we know for single Gaussian random variable, it is determined by two parameters. One is called mean, one is called variance, right? So the density is 1 over this guy. and the exp e to the power of minus 1 over this 2 variance times the square difference between your random variable and the mean. Okay. So, but here we want to be I want to advance our knowledge in that we want to be familiar with the multivariable case, because this is the most common used in machine learning scenario. So suppose we got a collection of random variables. Okay? So here x is a vector. It might be n variables, right? So if they follow a multivariate Gaussian distribution, in that they join follow a Gaussian distribution, then the density of this multivariate Gaussian distribution is determined by mean vector mu and the covariance matrix. Okay. If x is n-dimensional, then the covariance matrix will be n by n. Okay. Again, be sure that you are clear about the matrix sizes and vector sizes when you talk about vectors. Right? So, so the form of the probability density is as follows. So you're gonna multiply 2 pi sigma, sigma is covariance, right? You take the determinant of this matrix and take the power of a minus half. Then you multiply this exponential term, and now the power is a quadratic term. It's x minus mu transpose sigma inverse x minus mu. Another commonly used notion for this is to convert it as a trace operation. Right? Remember, when we talk about trace, it has a nice property that you can rotate the elements inside the trace, right? So you can rotate it here. It's a say A, B, is you can rotate it here, like B, C, A, right? So here, because this is a scalar, you take a trace, it is self. So you can put a trace from that, and then you move x minus mu in front of it. You end up equivalent notation, which is just trace x minus mu transpose, and sigma inverse. Okay. So those are two commonly used notion to represent density. And sometimes people might not use the covariance matrix as a parameter. Instead, they look at the inverse of the covariance matrix. Why? Because if you just memorize the inverse of covariance matrix, then in your power of the exponential, right? So here it becomes a lambda, right? You don't need to take a inverse, right? So that's another way to parameterize the Gaussian distribution. So inverse covariance is also called precision matrix. So here are a few examples of multivariate Gaussian distribution. Suppose in the 2D case, so if you see a circle, right, a great circle, regular circle, this usually indicates identity covariance matrix, or some constant multiply the identity covariance matrix, identity SL covariance matrix. But if you say it becomes an ellipsis, meaning x-axis and y-axis have a different length, but its axes are still in parallel to the horizontal and vertical lines, then there's still a diagonal matrix, but they have different elements in the diagonal. For example, 0.8 and 0.2. But in general, in most general case, what you're saying is just some kind of ellipsis. They can be inclined. That basically corresponds to the covariance matrix, which is dense. Maybe something like that.
Can we say that when the covariance matrix is there, it will exponent is to the independent?
Yes, yes, exactly.
So what is the indication of identity?
Identity, you you can see the identity matrices here, mean that the covariance of x1 and covariance of x2 is the same, right? So that's why I say it's identity, or identity times some constant, see 0.8, 0.8. This could show up a kind of regular circle.
X1, X2 have more strong.
In this case? No, in this case, x and x2 are independent. And in this case, x1, I mean, in both cases, B and C, x1, x2 are, they have zero covariance, right? So that's why their covariance matrix is diagonal, right? And that's where you see this is your density. The density function will look like that, right? And but this can be seen like from here, right? If this guy is diagonal, right? That means this part, the off diagonal element is 0. Only in this case, you can say this regular circle, regular ellipsis, where their axes are kind of in parallel to horizontal line and vertical lines, right? If it is not, this is the most general case you see, some kind of inclined ellipsis. I mean, you can double check with the definition here. Right? Double check the form. If it is a diagonal, say 0.1, 0.1, right? And two-dimensional case, it is correspond to this. If it is 0.8, 0.1, 0, 0 of diagonal elements correspond to this. If in the general case, it's correspond to this. Right? So just double check that.
In previous slide,
Mhm.
I wanted to mention just a typo. The power 2pi should be minus 10.
No, that's right.
For two-dimensional.
No, it's for n dimension. Yeah, why? Because I multiply 2pi to this matrix and then take the determinant. If I want to take 2pi out, yeah, you need to take power. Yeah, just be careful about that. I know someone will get confused at this point. Right? Thanks for mentioning this. Okay. Oh, by the way, any question about that? Yeah, I hope everyone is will get very familiar with this after this class, because this is really important. Right? Okay, so then let us talk about the MLE estimate for multivariate Gaussian distribution. Okay. First, from the multivariate Gaussian distribution, we can get two key facts. First, the mean of your distribution is mu. Right? So if your x parameterized by this mu and sigma, then from the density function, we can show that the mean of x is mu, and the expectation of the autoproduct of x, meaning xx transpose. So this is a n by n matrix. Is a sigma covariance matrix plus mu times mu transpose. Okay? So I believe you have shown that in your homework 0. And now, suppose we're given big N observations, ID, right? Identically distributed, independent, right? And the variable is d-dimensional, right? So we want to estimate the parameters mu and sigma from this data. How can we do that? Following the MLE principle, right? We can take a logarithm of this likelihood, right? So the likelihood, first I want to rewrite times right? This is the density, right? So if you compute the log likelihood over all the n variables, you just simply take logarithm of this density for each observation. You end up with this, right? So this guy is constant because you move 2pi out of this determinant. Of course, you need to take power, as I just mentioned, right? And then there's minus n over 2 logarithm log determinant of the sigma, and subtracted by a summation of big N quadratic terms, right, which are from the power of the exponential term, exponential in the Gaussian density, right? So you see that actually, if you want to get the mu and sigma from the data by using this MLE, you actually don't need to memorize all the data points. All you need to do is to calculate these two terms. And this is called sufficient statistics. So what is sufficient statistics? Just means that, okay, if you are given a set of data points, a set of observations, from this set of observations, I want to estimate the parameter of my distribution. The example is Gaussian here, right? So in many cases, I don't need to memorize or store the whole bunch of observations. What I need to do is just store several statistics. And using these statistics, I can get my estimate of the parameters. Here, it will correspond to mu and sigma. Right? So such kind of statistics is called sufficient statistics. You can view kind of like a summary of the data. And here you can see that this sufficient statistics essentially is just summation over all the observation and also summation over the outer product of each observation. Right? So to see this, why they are sufficient statistics, right? We can just take we can just look at MLE, right? Maximum likelihood estimation of the multivariate Gaussian. So as the name suggested, we want to maximize the likelihood. So we take the derivative or the gradient of the log likelihood with respect to the mu and with respect to the sigma, right? And we set the gradient to 0. We solve that equation so that we can get MLE estimate, right? So if you first take the gradient of the log likelihood with respect to the mean parameter mu, the gradient will be like this. Okay? So I believe everyone after homework 0 will feel it's pretty straightforward to get this. Okay? And now, if you want to solve this equation, you can get your MLE estimate of mu, which is the average of all the observations, right? So if you track to the first sufficient statistics, which is summation over all the xn's, you just now divided by the number of observations, you get your MLE estimate of the mu, right? And similarly, to get the MLE estimate of the covariance matrix sigma, right? You just take the gradient of the log likelihood with respect to sigma, right? And now you can see why you need to know some basic rules to compute the derivative with respect to log determinant, with respect to inverse of covariance matrix. They're all very useful. Okay? So, and I do believe after homework 0, these are pretty straightforward for everyone. So just list the result. So this is the gradient. And if you set this gradient to be 0, remember, mu here has been replaced by its MLE estimate. So you can get your MLE estimate of the covariance in this form. So it's just a summation over the outer product between each, between the difference between each observation xn and its MLE estimate, and then sum over them and then take the average. So this guy is the same as this guy. Okay. So if you just, expand this auto product and do some term arrangement and cancel something out, you'll end up with the same thing. These two are these two are the thing. So you can see that this is the second sufficient statistics, right? As we just mentioned here. Right? So that's why you can see that by just using these two statistics, you can get your MLE estimate for the mu, MLE estimate for the covariance matrix. And another observation is that this MLE estimate is nice because it is a semi-positive definite. Remember, by default, we're going to assume your covariance matrix must be a semi-positive definite, right? Otherwise, it's not valid Gaussian distribution. So I want to point out a fact. MLE estimate is also a random variable. Why? Yes, exactly, right? So just be aware of this fact. First, the MLE estimate of the mean is an average of the data, right? The data itself is random, so mu of ML is random. And second, if you look at this, it also depends on data, right? So you can view both mu and sigma, their MLE estimate, as some function of your observed data, right? Because these data are random, so their function is random as well. So, and then naturally people want to ask, right? So do this estimate, are these estimates biased or unbiased? Unbiased means that although this comes from some kind of operation over the observed random variables, right? If I can ensure that I take expectation over this guy, it is exactly the same as the truth, the ground truth mean. Then I call it as unbiased. Right? So for mu estimate, right? We know that it is just the average of each observed accent, right? So if you take expectation of mu ML, it is take expectation over the summation, right? You can just move in. This guy is mu, right? So you just average a set of the same expectations, it will end up with the ground truth mu. So that means, okay, the MLE estimate for the mean parameter mu is unbiased, right? Because I take the expectation on my estimate, it gives the ground truth, right? I believe everyone has heard this concept before, right? Unbiased and unbiased estimate. Right? So if you're uncomfortable, just let me know. Okay, so basically, we need to first realize that all kind of estimate. This is just one possible way of estimate parameters. Right? It's called MLE. You might have like all kinds of weird way to estimate those parameters. So in MLE, you're gonna maximize log likelihood. Maybe in other way, you got your own estimate, right? You might have other way. That is depends on how you define the function over the observations, right? It can be here, it can be average. In other places, it can be just median, right? So then how do we compare the performance of different estimates, right? One measurement is to look at if you take expectation of your estimate, if it is still the same as the ground truth. Right? If it is same as the ground truth, then we call this estimate is a unbiased estimate. Why? Because although it's random, right? Also it's random. You can will like, okay, after I collect one bunch of data, I got this estimate. After I collect another bunch of, I got this estimate, right? No matter how it perturbates, right? You can imagine if I do this estimate 1,000 times on average, they kind of converge to the ground truth. I don't want after 1,000 times estimate, they kind of still deviated from the ground truth. That's not good. Right? So, so that's why they always check if your estimate is unbiased or biased. Right? If it is unbiased, well, it's a good property. Right? But for MLE estimate, the unbiased estimate is only for the mean. For the covariance, unfortunately, it is biased estimate. That means if you take expectation of your covariance estimate, it will not give you the true covariance. They give you a true covariance multiplied by this factor, n-1 over n. Okay. That means, okay, your estimate is on average is still less than the true estimate. So kind of like underestimate the covariance, right? This is a very well-known result. So, and how do you get this conclusion, right? So I will give you a hint because it's very likely to be included in your homework 1, right? So if you take a look, if you want to derive the expectation of this MLE estimate of covariance, right? You just take a look at the form, right? So it's xn subtracted by mu, ML, so subtracted by mu, L, transpose, right? So just take expectation about this, right? So one way to show that is that I'm gonna subtract the true mean plus the true mean in these parentheses. Right? So now you take and you try to expand this. Right? You got this and this and this and this, and try to expand those 4 terms, and then you take expectation. You say why you're gonna have this extra factor. Then people kind of natural asking, right? So now that if I take the expectation of this guy, right, is n-1 over 1 times the true covariance, right? So what if I want to get an unbiased estimate? Right? Yeah, I just multiply the factor back, right? So that's why if you want to get an unbiased estimate, you will not divide this statistic by n, rather divide it by n-1. But of course, I mean, under a large number of samples, this difference might not be that important, because if n is very large, you can view n-1 over n is very close to 0, close to 1, right? That's why for the asymptotic property, right? Asymptotic property usually means that if n goes to infinity, if you have an infinite number of examples, how does this estimate approach to the true covariance, right? So in that case, it still converges to the true covariance, because this ratio, this factor converges 1. Okay. Yeah, before we proceed, any questions so far? I'm just repeating some conclusions from.
In the unbiased estimate, you still
I guess not. I haven't tried that. Yeah, okay, you can try that. Yeah, I wouldn't. I tried that a long time before, but you can definitely try that to verify that point. I don't know actually. I cannot confirm right now, because I cannot memorize that. Yeah, but definitely worth trying. Yes. Okay. So another very important computational trick regarding multivariate Gaussian distribution is how to partition that, and then compute the conditional Gaussian distribution, right? So this is the vector x, right? So you can imagine I'm gonna partition it into two parts, xa and xb. So xa and xb are two subvectors. So that when they concatenate together, you end up with x, right? So and correspondingly, your mu vector and your covariance matrix can be partitioned as well, right? So mu vector will have the corresponding mu a and mu b, and your covariance matrix can be partitioned as block matrix, right? Sigma AA, sigma AB, sigma BA, and sigma BB, right? So if we consider the precision matrix representation, you can partition the precision matrix accordingly as well, right? So if we write it down, right, XA and XB, your partition view of your normal distribution will be something like that, right? Right. So I believe everyone knows that if you look at the marginal distribution of each part, right, like P of XA, it will be simply mu A and sigma AA, right? But why is that? Right. Suppose we have already known XA and XB, they jointly follow this multivariate Gaussian distribution, right? How can we derive the conclusion that the marginal distribution of XA will simply correspond to the part, right? What?
Integration.
Yeah, of course, we can take integration, but that will make the things a lot harder. Yeah. So I want to introduce some kind of computation technique to answer this question. But this technique, is not only useful to answer this question, but also useful in applying a lot of applications and modern problems, right? So to answer this question, we're going to first take a look at, like, suppose we're not trying to calculate marginal distribution. We're trying to compute the conditional distribution, right? So suppose XB is given, right? What is the conditional distribution of XA given XB?
Joint over, you know that XP is normal distribution, you know the distribution is just.
Yeah, of course, this is a Gaussian. The problem is how do you determine the parameter of this condition Gaussian? Yeah. Okay, so here we're going to talk about a very useful trick. It's called completing the square trick. Very useful to deal with Gaussian-like distributions, right? So our key observation is that if you look at exponent of the general Gaussian distribution, for any Gaussian distribution, the density is always like something, you have a normalization factor times exponential things, right? And the exponent or power in this exponential thing is always a quadratic term, right? And now, if you just look at those terms, right, you know that actually you have only two terms regarding x. One is the quadratic term, the other is a linear term. And the other has nothing to do with x, you can view as constant. So that is, if you just expand this, right, you got x transpose sigma inverse x, and then, subtracted by 2 x transpose sigma inverse mu plus mu transpose sigma inverse mu, right? So you can see that you got a quadratic term to x and a linear term to x. So the quadratic term, the coefficient is essentially this inverse covariance, right? And for the linear term, the coefficient is sigma inverse mu. Right? So that means in whatever cases, right? In whatever kind of computation, if you know this is a Gaussian, you just if you want to check if this is a Gaussian, you just try to take a look all the terms regarding x. If it contains a quadratic term and a linear term, then it must be a Gaussian. And if you want to, for example, if after some kind of manipulation, right? If you got some term like x transpose s x plus x transpose a, you can use this form to map back to their parameters. Why? Because from the quadratic term, we know, okay, s must be, sorry, I need to put minus half here, right? So s must be sigma inverse, right? And the coefficient for linear term must be a sigma inverse mu, right? Now you can recover what is the parameter mu and sigma from your derivation. This is called completing the square trick. Now let us apply this trick to get our conditional Gaussian. So first of all, because we have some partition of this Gaussian, right? So we got mu A, got mu B, we got sigma, right? But here, because we're dealing with a sigma inverse, to be more convenient, we just look at the precision matrix, right? The inverse of covariance. And accordingly, precision matrix can be partitioned as well. So you can go as a partition a block version of your precision matrix partition in the same way. Okay. So now, if you expand the density of this giant Gaussian, right? So it will break up into 4 terms. So, I mean, to be more clear, remember this guy consists of 2 vectors. Xa minus mu A, xb minus mu B, right? This guy times this block matrix, right? Times, sorry, this should be transpose, right? This is xa minus mu A, xb minus mu B, right? If you write down this quadratic term, right, according to the partitions, it's something like that, right? And now you just, expand the summation, right? So you got like 4 terms, right? This guy, this guy, this guy, the first term, this guy, this guy, this guy, this guy, this guy, second term, this guy, this guy, this guy, this guy, and this guy, third term, this guy, this guy, this guy, and this guy, fourth term, right? It's just mechanical expansion, right? So now let us look at this form, right? Remember, we want to compute the conditional distribution of xa, conditional xp, right? So we only care about the terms regarding xa because we're looking at ace distribution. All the other terms you can view as some kind of constant. So if we look at the terms regarding xa, we first found a quadratic term from here, right? Right, because xa minus mu a here, xa minus mu a here, so it must have some quadratic term, which is given by half xa transpose lambda aa in xa, right? And then we know that this sigma aa must correspond to the inverse covariance of your conditional distribution, right? So which is denoted by sigma a given b, which is inverse of sigma aa, right? So then we can take a look at the linear term. So the linear term, you just look at who is going to multiply with XA, okay? So here, we know that XA transpose with this guy, right? Lambda AB, XB subtracted by mu B, right? And here they're gonna, you're gonna see it again, but it's just take a transpose. And third one, you know, the fourth one, this term actually does not contain XA at all, so you can view it as constant. So just merge the two terms, you got your linear term, which is sigma AA, mu A. Oh, by the way, here you got, first of all, you got a linear term for XA as well, right? Because you got mu A transpose sigma AA times XA, right? So you find that you can merge the linear term together, you get the sigma AA mu A subtracted by, not sigma A, lambda AA mu A subtracted by lambda AB XB time, subtracted by mu B. Right? So now we got the coefficient for the linear term. Right? Now, as we just mentioned, right, for any Gaussian distribution, it is determined by a quadratic term and a linear term. We have already found the coefficients for these two terms, right? So we can use them to map back to the corresponding mean and covariance. So this is a linear term, and from the Gaussian property, we know that this is corresponds to a covariance inverse times mu, right? And covariance itself is here, right? And here we know that it is sigma AA inverse. This is something we just mentioned before, right? So we can just multiply it back. We got your conditional mean, which is mu A subtracted by this guy. So finally, by leveraging this completing the square trick, we get our conditional mean and conditional covariance. So if you don't, is everybody comfortable with the general sense? I'm not requesting you to follow exactly every step because it might take a little bit more time. But I just want to give you the general sense. We just want to match the form of the general Gaussian. It must contain some quadratic term and a linear term. And then you want to extract the coefficients for those two terms. Use coefficients to map back to the mean and the covariance parameter. Does it make sense? Right? And then the remaining thing is just tedious thing. I'll highly suggest you guys to look at the slides and then derive it by yourself, because we won't spend like 20 minutes to do that. It just give you the conclusion. So by applying this the square completion square trick, we can get your conditional Gaussian. It has mu conditional mean and conditional covariance in this form, right? And again, let me emphasize this lambda is the inverse covariance for the whole joint distribution, right? And the lambda AA, lambda AB, lambda BA, and the lambda BB are just the corresponding blocks, right? So the remaining question would be, okay, how can I get lambda AA inverse and the lambda AA inverse lambda AB? All from the covariance matrix sigma. Right? So yeah, let me emphasize this again, right? So this is a block version. If you take the inverse of the whole covariance matrix, you get your precision matrix. Right? So now we want to obtain each block in the precision matrix in terms of the covariance matrix. Here we're going to use a very popular and important property. It's called block matrix inverse. Right? So again, you don't need to memorize this, but you just keep it in mind. If I block matrix in this way and this matrix is invertible, then you can partition the inverse in the same way, and each block can be represented in these formulas. Okay, so if you apply this, okay, we can immediately get like sigma lambda AA here is sigma AA subtracted by sigma AB, sigma BB inverse, and sigma BA. It's kind of like clockwise rotation. Okay, and this lambda AB, of course, it has a more complex form, but anyway, it's just a straightforward application of this guy. Okay. Now you substitute these results for lambda AA and lambda AB in the things we just derived. You finally can get your mu conditional mean and conditional covariance in this form. This is something you can find from Wikipedia. If you look at, if you just search multivariate Gaussian and click into the Wikipedia, they're gonna give this, right? But they won't tell you how this is derived.
So, given x, so how did you write XA given XB?
XA what?
How did you write XA given XB?
How do I write XA given XB?
Yeah.
It's here, right? So this distribution tells that the probability density of XA given XB. So,
I mean, I'm saying, how do you know XA given XB is probability?
oh, if you take a look at where is it? Expansion, right? Remember, we take a look at XA given XB, right? If you just take a look at XA terms, it only contains a quadratic term and a linear term. That determines that the conditional distribution will be a Gaussian as well. Yeah, it's a form. It's a form which determines XA is XA conditional XB is still Gaussian. Okay, so now with the same trick, you can show that the marginal distribution of XA will be this mu A and sigma AA will be determined by the mu A and sigma A accordingly, right? So I will leave it as an exercise for you guys. I highly recommend you to practice this square completion trick because it's really, really useful in probabilistic modeling. Why? Because nearly all the continuous random variables, continuous observations are modeled by some kind of Gaussian distribution. And when you do some inference, when you do some calculation, those tricks is kind of critical. Otherwise, if you want to do the integral, those kind of things by yourself, that will be a lot harder. Okay. So the next distribution we're going to talk about is called gamma distribution. So if you look at the scalar Gaussian distribution, right, we know that it is parameterized by mu, but also parameterized by the variance, right? So the question is that, what if I want to assign a prior over the inverse of the precision, or inverse of the covariance, inverse of the variance, namely precision? What kind of proper distribution for that, right? So here I'm talking about assign a distribution over the inverse of the variance, or in other words, precision, right? So a very commonly used distribution is gamma distribution. So of course, because this is a covariance, it must be a positive, right? That means you need to give a distribution which can only place probability or densities over positive numbers. They cannot place densities over negative numbers. So here's a form of the gamma distribution. It also determined by two parameters, A and B. And terms related to the variable lambda here is lambda to the power of A minus 1, e to the power of minus B lambda. So it's kind of resembles exponential distribution, but it's different because we have this extra lambda to the power of A minus 1 term. Okay. And the gamma distribution has, two types of representations. And we use this skew and rate parameterization. But in some cases, you're going to say they use A and O1 over B to parameterize gamma distribution. This is just another way to parameterize that. So don't feel weird. We use this just for convenience. So here are a few important properties of gamma distribution. The expectation of your gamma distribution when the variable is A over B, and the variance is A over B squared. And if you take a logarithm of your random variable and takes the expectation, now you will meet this digamma function again. Right? It's a digamma of A subtracted by logarithm of B. Sorry, this should be unbolded in. So, of course, different choice of A and B will will give you different shape of the density function. For example, A and B are both 0.1, so the density function will be like this way. If A and B are both 1, it will be more, it will be flatter. If A is 4 and B 6, you know, it's resembled like some kind of a mode, right? So that is interesting property. If the random variable lambda follows a gamma distribution, then the inverse of lambda follows so-called inverse gamma distribution, and they have the same parameters. Right? So what's the usage for that? Right? So as we just mentioned, right, gamma distribution is really used to model the inverse of the variance, right? Someone might feel pissed off about this, right? It's not convenient, or it's not natural. So people would ask, what if I want to assign a distribution, a prior distribution over variance directly, rather than its inversion, right? Then you can use inverse gamma distribution. It's kind of the same thing, but one is one way is you can deal with inverse of variance. The other is that okay, I directly deal with the variance. Okay, V-short distribution. So if we switch to multivariate Gaussian distribution, the gamma distribution, when we talk about this, about scalar Gaussian distribution, right? So its x is just a number, it's just scalar. What if we want to deal with multivariate Gaussian distribution, right? In the multivariate Gaussian distribution, now the variance becomes a covariance matrix. Right? What if I want to assign a prior distribution over the covariance matrix, or its inverse? Right? Again, we can talk about the inverse first, right? That is, if you want to assign a prior distribution over the precision matrix, inverse of covariance, right? What is the common used distribution? The common used one is called V-short distribution. V-short distribution. Right? So here is the density form of V-short distribution. Of course, no one is required to memorize that. I can't memorize that, although I first say this guy like 10 years ago or 15 years ago. I forgot, but I can't memorize that. Like, every time I need to look at the Wikipedia. Right? But anyway, just to keep in mind that the V-short distribution, they are parameterized by two parameters. One is this called skew matrix, it must be positive definite. The other is called degree of freedom. The degree of freedom nu must be no less than the dimension of your x. And I'm not going to talk about this constant, this multivariate gamma distribution. So again, it's kind of similar to the case of gamma distribution. If some matrix lambda follows the V-short distribution, then its inverse follows the so-called inverse V-short distribution, and these two distributions are parameterized in the same way. So inverse V-short distribution is often used as prior over the covariance matrix of multivariate Gaussian distribution. So if you want to incorporate some knowledge to estimate covariance matrix, okay? Not only from data, but also from your own experience, then the inverse Wishart distribution or Wishart distribution is a good choice. Okay, so let us stop here today and see you on next Tuesday.